Michio Honda from University of Edinburgh. Storage systems such as file systems and databases are primary home of your data. To keep the data after power cut or reboot, they store the data in a persistent storage medium, such as hard drives, SSDs, and persistent memory. In traditional storage systems, software overheads are not dominant because access to the hard drive or SSD is slow. However, emerging storage media, persistent memory, is much faster than hard drives or SSDs. As a result, software overheads in the storage system impact end-to-end performance. Also, hard drives and SSDs are block devices, which means that applications need DRAM buffer caches and system calls to access persistent data. On the other hand, persistent memory is byte addressable. This means that applications can access persistent data just using load and store CPU instructions, without buffer caches or system calls. Therefore, many storage researchers design efficient persistent memory systems using those unique features. Where do the storage software overheads come from? They come from achieving storage properties. First example is integrity, which ensures that data is intact over time. Integrity is typically achieved using checksums. The second example is consistency. The data must be consistent in the presence of concurrent readers and writers. The data also must be consistent after crash. The third is searchability. Data must be found and returned to the client quickly when requested. Achieving those storage properties is the major source of software overheads in the storage systems. When persistent memory storage systems need networking, they typically use RDMA because it gives more CPU cycles to storage software. However, it is quite inconvenient because storage clients cannot always use RDMA. Therefore, in this work, I ask a research question. Can we enable efficient networked persistent memory systems without RDMA? What are design options to reduce the network storage software overheads without RDMA? First one is in-storage computing, which is popular in SSDs implemented as PCIe devices. This approach is unlikely feasible for persistent memory because they are not PCIe devices. The second approach is the use of external accelerator devices such as GPUs. This approach is also unlikely feasible because it needs additional data movement. My approach is repurposing networking features which are available in reliable transport protocols and network stacks to implement storage properties such as integrity, durability, consistency, and searchability. For example, when we look at TCP headers, we already have checksums, timestamp, and sequence numbers. Therefore, we could reuse those features to implement storage properties. Also, many networking features such as checksum calculation, segmentation, and timestamping can be offloaded to the NIC hardware. One design rationale is that both reliable network protocols and storage software are designed to survive dumb faulty hardware. Networks are dumb and faulty because they reorder, drop, and corrupt packets. Storage devices are also dumb and faulty because they reorder writes, corrupt data, and return unreliable responses. Networking and storage software needed to be designed in isolation because Networking software uses in-memory data structures, although storage software uses on-disk data structures. However, persistent memory data structures are much closer to in-memory data structures than on-disk data structures. Therefore, at a high level, it would be possible to more closely co-design network and storage data structures. We can also find that packet representation in the network stack is quite flexible and optimized in memory data structures. It can represent data larger than a single packet, which is across multiple memory pages. Such large data is split by TCP segmentation offload. A TCP receiver organizes out-of-order packets in a red-black tree to find relevant data quickly. This indicates flexibility of packet metadata structures. Various pointers such as those to sockets and protocol headers are also available. Packet metadata can be replicated without copying data using a clone. A TCP sender uses this feature to keep the original metadata until the packet is acknowledged by the receiver. To see whether repurposing networking features would really reduce storage software overheads or not, I wanted to confirm the overhead to achieve storage properties are really high. I ran an experiment using a modern network and persistent storage stack with a real persistent memory device. For the network stack, I use paste because it achieves high performance without losing in-kernel TCP functionalities. For the storage stack, I use NovelSM because it is a free storage stack based on widely used LevelDB and optimized for persistent memory. The networking latency, including TCP and HTTP, was 26.7 microseconds. This is an application level round trip time. Once the request goes to the storage stack, request preparation takes 0.7 microseconds. Checksum calculation takes 1.7 microseconds. Data copy takes 1.1 microsecond. Buffer allocation and insertion takes 2.7 microsecond, and persistence takes 1.9 microsecond. In total, the round-trip time was 34.7 microsecond, and within that, 6.2 microsecond is spent as data management overheads to achieve storage properties. Is that data management overhead really significant? This is true. I compared two cases with and without data management overheads. We also use concurrent TCP connections. Here is the result. In the left figure, I confirmed that latency impact caused by data management overheads can be hundreds of microseconds, and in the right graph, throughput penalty can be up to 28%. Those penalties are because of request backlog increased by data management overheads. I conclude that data management overheads are significant. There are a lot of interesting research agenda. First, we have to make packet metadata structures persistence friendly. Second, in addition to obvious techniques like checksum offloading, we should think about other NIC offloading opportunities useful for both networking and storage. Finally, we should also think about other reliable transport protocols such as HOMA and QUIC. Thank you for watching. Please read the paper for more technical background and details. You can download the paper from my website.